Hello, my name is Scott Landau, and this is the Physics 2212 Lab 4 report. So for the introduction, the purpose of this lab is to both examine behaviors of circuits containing resistors and capacitors, as well as measuring experimentally the voltage differences in conventional currents in something such as the circuit that you see below. The main physics principles we're going to look at are Kirchhoff's laws, which was the node and loop rules, Ohm's law, capacitance, and series and parallel circuits. And you can see an example of a series circuit and a parallel circuit in the image to the right. In this experiment, the system is a circuit and the surroundings, the rest of the universe, as we're just focusing on only the circuit. And the initial conditions of the circuit varies. The capacitor is either charged or discharged, and the circuit's either in a steady state or not, based on whether this capacitor is charged or discharged. And in the actual experiment, um, in this one, the charge and energy conservation, the setup is two batteries, two resistors, and two ammeters. And readings from the ammeters were conducted. And using Ohm's law, current flow is able to be predicted. And was compared with the ammeters and got consistent results of 0.03 amps. And you can see just the typical Ohm's law on the bottom right. And we conducted another experiment with a new setup where there was two batteries, two resistors, one ammeter, and one voltmeter. So one of the ammeters was replaced with a voltmeter. So we were able to read off of both of them. And using Ohm's law to predict the current flow and voltage, and then we compared it with the ammeters and voltmeters and got pretty consistent results of um, essentially no current and then 3 volts. And then this continued. We did another experiment with two batteries, two resistors, and one ammeter, and recorded at every point in the circuit. And using Ohm's law to predict the current flow and voltage again, like compared with the simulation that we ran on our own time to see if it was the same. We got consistent results of 0 round trip because it ends up at 0, which is what we want because we want the total round trip net voltage to be 0. And then for an RC circuit, we have two bulbs, a battery, a capacitor. We used a watch and a voltmeter, and we recorded the time it took for a capacitor to charge the stopwatch, or to charge the light bulb with the stopwatch and read the voltmeter. And we used capacitance to predict what would happen to the bulb, and experimental values were consistent. And the bulb dimmed while charging and discharging. And we got 15 seconds for 10 ohm bulb and 29 seconds for 20 ohm bulb, which was consistent with the formula C equals Q over V. It continued in the new setup. We had two bulbs, a battery, a capacitor, a watch, and a voltmeter. Recorded the experimental values of the natural log of V over V naught at the time intervals and plotted to calculate their slopes. And in this, an experimental value was found to be about negative 0.167 slope, which equated to about 6 seconds using the RC formula. Some potential sources of errors were inaccurate measurements, and like the light bulbs and resistors and wires could have been damaged or something like that, creating inaccurate data. And what if we did this lab in real life? Well, we did this lab in real life, and so we looked at the virtual circuit and determined how it would behave, and it was very similar, except the real ammeter had some resistance, so it had a lower experimental value than the online one. And then what if um since we were completing the lab with real circuits, we used an ammeter to measure how long it would take to charge the capacitor when connected directly to the battery, and in real life it charged it almost instantaneously. Online it was going to be in 0 seconds, but since we don't have a battery that can do that, it was almost instantaneously. Thank you for listening to my lab.